All right, let's get started. So what I showed you was a demo of learning a function from data. And essentially the message I was trying to give you is that learning a Gaussian process is very easy. Maybe understanding what it is a little bit tricky, but learning it from data is incredibly easy. It's just a few lines of MATLAB. And even if you use different covariance functions, predictions can be quite similar for, these are a single sample from the prior for different covariance functions. These are the mean and the standard deviations for the posterior, given this data in blue. And the predictions are all quite reasonable. Okay? So let's talk a little bit more about Gaussian process covariance functions. So again, here is a sample from a Gaussian process. And the kernel, we can think of it as, we can sort of think about it as an n by n matrix if we have n data points. So in particular, imagine for now that we were sampling our function equal distant points n times. Okay? So f1 through fn look like this. Okay? Then this kernel evaluated at those n points would be an n by n matrix. Okay? And it would kind of look like this, right? Where the magenta areas here are high covariance, high correlation, and these greenish blue areas here are low covariance or low correlation. Okay? So what does that actually mean? That means that nearby points are going to be similar. That's in the sort of magenta region. But far away points are going to be roughly independent. That's in these regions. Okay? So in particular, if this was high values near 1 and these were values near 0, that would exactly capture that sort of structure. Now, in general, a covariance function, there are many different choices of covariance functions, or also you could call them kernels. And they have hyperparameters. These are these things in blue. So for example, there might be an overall magnitude multiplying the covariance function. That gives you the magnitude of the function. And there might be length scales. And if a function is living in d dimensions, here we're just showing it living in 1 dimension. If the function lives in d dimensions, then there might be d different length scales. Okay? So there are a bunch of hyperparameters in the covariance function. And these are just the expressions, again, for Gaussian process regression. Imagine you have some sample data that might look like this. And then, if you want to make predictions, the predictive mean is obtained by kind of a one-line expression here involving some matrices and a matrix inverse and multiplying that by a vector on this side and on that side. Okay? And the predictive variance is also obtained by an expression like this. And I'm not going to go into detail in how to derive these expressions. It's just manipulations with Gaussians. And there's a lovely textbook that you can look at, if you want to get more of the details. The basic message I want to give is that it literally is just a couple of lines of MATLAB to produce these predictions from these Gaussian processes. So let me actually let me point you to a very useful resource, which is that book that I was referring to. This is a great book. It's called Gaussian Processes for Machine Learning. It's in fact available completely online. So you can just download it, or if you want, you can buy it, pay money for it. if you want the hard copy. Probably cheaper than printing it out in color. It comes with software, which is called GPML. So if you just if you search for GPML, you'll find this software in MATLAB, and we'll do maybe one of the demos for this software. It's very, very easy to use as well. Okay, so let's talk a little bit about learning the kernel. So here I have an example of a kind of kernel, and how do we parse this thing? Well, it's a function of two locations, xi and xj. Okay, and in fact, most kernels tend to be functions of the distance between xi and xj. So the further away xi is from xj, the lower the covariance would be in most functions. And in fact, xi and xj could be vectors. So maybe that's that function depends on the distance between xi and xj along each dimension differently. So maybe the function depends a lot on dimension 1 and not so much on dimension 2 and not so much on dimension 3, etc. Okay, so D here indexes the dimensions of x. And remember, the definition of this thing is that k of xi xj is the covariance between f at xi and f at xj. Okay? In some sense, how similar is f at xi to f at xj under the distribution? Okay? So, so this covariance function has a bunch of parameters in it. So in this case, there is a parameter here, v0. There are d parameters here. These are the length scales for each of the different dimensions. There's another parameter here, alpha. And there's another parameter here, v1. Okay? These mean different things. I could spend about 10 minutes explaining to you what these things mean. Or you could draw samples of Gaussian processes with these different covariance functions and understand what they mean, just because it's, it controls different aspects of the function. But what we're really interested in is learning these things from data. So given a data set D, how do we learn these parameters theta? Okay? And the basic idea is fairly straightforward. We can actually compute the marginal likelihood for the data as a function of theta. So we know that our observed y values, remember we're mapping from x to y, our observed y values given x as a function of theta is drawn from a multivariate normal distribution, where theta appears inside the kernel here. So the log likelihood, the log marginal likelihood, is a function that looks like this. And we can actually simply optimize this as a function of theta. Okay? Or if we wanted to, we could be a little bit more Bayesian and infer theta from the data. So actually come up with a distribution on the hyperparameters from the data. Okay? So in a few minutes, I'll show you some demos of learning the Gaussian process hyperparameters from data, because it's sort of fun to see what it does. But right now, I want to tell you a little bit about the relationship between Gaussian processes and linear regression, which is pretty interesting to understand, and also between Gaussian processes and support vector machines. So let's talk about linear regression. So imagine you start with a linear regression model where you have inputs xi and outputs yi. That model might look something like this. Yi equals beta 0 plus beta 1 xi plus epsilon. So that's just a linear function with some parameters beta. Okay? Now, this is a linear model. That's kind of boring. So here's something we could do to make it a little bit more interesting. Instead of making y a function of x directly, we take basis functions, call them phi of m, evaluated at these different x, and we make y a linear function of these basis functions. Okay? So for example, the basis functions might be anything you want, really. So, you know, I'll give you an example. So instead of saying y equals beta 0 plus beta 1 x plus epsilon, I'm going to say, okay, let's say y equals beta 0 plus beta 1 x plus beta 2 x squared, right? Why not? Plus beta 3 sine of x plus beta 4 log of x, whatever I want, okay? So the basis functions here, the first basis function is 1, okay? This one is x. This one is x squared. This one is sine of x. This one is log of x. Okay, so we could call this phi 1 of x, which is a constant, phi 2 of x, etc. Phi 3 of x, etc. So polynomial regression is just a special case of what I've called basis function regression here. By basis functions could be sinusoids, and so then it would be like a kind of harmonic analysis, maybe. Okay, so that's a little bit more interesting. The nice thing about this model is I can still solve for the betas analytically if epsilon is Gaussian. If I fix the basis functions, then this is a linear system of equations that I'm solving. Okay, so now let's do something a little bit even more interesting. Instead of optimizing the betas by doing something like maximum likelihood, let's put a Gaussian prior on the betas. So these coefficients, I'm going to say I don't know what they are. I'm going to learn them in a Bayesian way. I'm going to start with a Gaussian prior on them, maybe a very broad Gaussian prior. And then when I observe some data, my posterior will be more concentrated around reasonable values for these coefficients. So here is a Gaussian prior on my basis functions. And now the interesting thing is having assumed a Gaussian prior on these basis functions, I can compute the mean of y. Let's say these were all zero mean Gaussian priors, then the mean of y would be 0. But I can also compute the covariance between any pair yi and yj, call that kij, and that's expressed in this following form. That's just given by the variances of my Gaussian distributions on the beta. These are these lambdas. And then the dot products of these phi functions. Okay. And in fact, the distribution on y defined by this model is a Gaussian process with zero mean and that covariance function. Okay. So, so this is a way of going from linear regression to Gaussian processes. This step is already a Gaussian process. And in fact, this is a Gaussian process with a finite number of basis functions, m, but many widely used Gaussian processes correspond to this sort of argument, but with infinitely many basis functions. Okay. So that's one relationship that's interesting. Another relationship that's interesting is a relationship determined by Radford Neal in 1990, well, actually in his thesis in 1992, but that appears in his book in 1996, is the relationship between Gaussian processes and multi-layer neural networks or multi-layer perceptrons. And that relation is that a multi-layer perceptron with infinitely many hidden units and Gaussian priors on the weights in the limit becomes a Gaussian process. Okay? So now, you know, instead of worrying, well, how big should I make my neural network? You could say, make it infinitely big and solve it with 2 lines of MATLAB. Right? Instead of making it, you know, 100,000 neurons and worrying about using, you know, fancy computers and so on, the infinite limit is this Gaussian process. So that's also very, very interesting. And that's been known since the early 90s. Okay. Now, I've talked about Gaussian processes for regression because that's easiest to understand to start out with. But Gaussian processes can also be used for classification. And the idea of Gaussian processes for classification is the following. So imagine I had a prior on functions. This is a sample from that prior on functions. Now I could simply consider places where the function is positive to be places where I'm in the positive class, and places where the function is negative to be places where I'm in the negative class. So if I'm doing classification with 2 classes, +1 and -1, then I simply put a Gaussian process prior on functions, and then I map from the function value to something like the probability of being in class 1 or class -1 at any input location. So this is a picture in 1 dimension if I was doing classification in 1 dimension. This is a picture in 2 dimensions where, you know, I have some data, and basically this is the red area is class 1 and the blue area is class 2. And the way you need to think about this is there is a function, okay? It's an unknown function, but under the posterior, the unknown function is underwater in the blue area, okay? And there is an island, you know, there is some islands that come up in above 0 in the red area and then go back underwater in the blue area, okay? So just, you know, where that function crosses the 0 point determines the decision boundary of going from positive to negative class. This is in 1 dimension, this is in 2 dimensions. The generalization is obvious in higher dimensions, and it's just as easy to use in higher dimensions. It's just not very easy to plot in high dimensions. Okay? So there are many ways of relating the function value fi at a particular point xi to class probabilities. So for example, you could run the function value through a sigmoid, and that's how you could get the probability of a class being 1 or 0, or a cumulative normal, or just simply a threshold function like I've done here, or some other version of you know, some generalization of a threshold function, etc. Now, the problem is, before we had a Gaussian process prior, we had conjugacy, right? We had a Gaussian process prior and a Gaussian likelihood, and that gave us a Gaussian process posterior. Now we have a Gaussian process prior, but some likelihood function that looks non-Gaussian as a function of f. Okay? So when you multiply a Gaussian by a non-Gaussian function, the posterior on f is going to be non-Gaussian. So it's not conjugate anymore, and we need to use approximate inference methods to solve that. Things like, and I've described all these methods already, things like Laplace's approximation, or variational Bayes, or expectation propagation, or Gibbs sampling, Markov chain Monte Carlo. All of these methods can and have been applied to Gaussian processes. Okay. Okay. I want to draw a picture for you, which maybe is useful to think about. In probabilistic machine learning, there's a very nice distinction between models and methods. Okay? So, for example, models might be something like, directed graphical model or something like that. That's one thing we've studied. The model might be something like Gaussian process classification, right? Or a model might be something like, logistic regression. Or even like a Bayesian neural network. So a neural network where you just try to do inference over the weights in the neural network using Bayesian inference instead of optimization. Now, methods are methods for doing approximate inference. So your methods might be MCMC, variational Bayes, EP, BIC, Laplace, for example. Now, it turns out, for every model, if it's a non-trivial model, there's some non-trivial integral that has to be done. And you can probably, try doing it in all of these different ways. Okay? In fact, I can probably think of papers for each one of these edges here. Okay? Like, there is a famous paper that tried doing EP for Gaussian process classification. Unfortunately, they've all been done. So, you can't publish a lot more papers just by filling in missing edges here. But, there was a paper that showed that EP compared to these other methods worked best for Gaussian processes, okay, for classification. So that's interesting. Radford-Neal's thesis in 1992 was applying MCMC to Bayesian neural networks. David Mackay's PhD thesis in 1993 was applying Laplace's approximation to neural networks. Okay. So, but it's nice to distinguish between models and methods. First, you think about, well, what's our model? Okay. Once you write down the model, then there's some difficult bits in the model, but the model makes predictions about data. Now, the difficult bits you can handle in different ways depending on your speed-accuracy trade-off. Okay? Some of these methods are fast and inaccurate, like BIC. Some of them are slow and potentially more accurate, like MCMC. Okay? All right, so this is Gaussian process classification. Let me explain to you the relationship between Gaussian processes and support vector machines. So again, I know I've asked this question before, but just remind me, how many of you have studied support vector machines at some point? Okay. All right. So I will describe it first with a picture, which I drew a couple days ago. Okay, so here is a caricature. So SVM is a combination of two very important ideas. One of them is called the Kernel Trick, and the other one is called maximum margin. Okay, so the kernel trick is as follows. Imagine you have a linear function or some method that is linear. So for example, for regression, it might look like this. For classification, it might be y is some threshold function. Let's say this is a threshold function applied on beta transpose x. Okay? So it's linear followed by a threshold here. So now the kernel trick says, instead of thinking of a linear method, map my data, my input dimensions, into some feature space phi of x. Okay? In fact, we've seen this kernel trick before. Where did we see this? What did I call this before? Anybody remember? Somebody. Please remember.
I don't remember the name. Base function.
Basis functions, yeah. Before I called them basis functions, now we can call them feature map or a kernel trick. So all of these terms have been used before for the same idea. Just take your data and map it through some functions to a new space. And in fact, the interesting thing is, instead of doing dimensionality reduction, usually what we want to do is dimensionality expansion. So we take our original data and we map it into a very high dimensional space, maybe even an infinite dimensional space. And then we apply our linear method in that high dimensional space. So why would we do that? Anybody know? What's the point of doing that? Sorry? The XOR problem, for example. Yeah, okay. Yeah, but give me more of an intuition. So in general, what is, maybe somebody from this side of the room. What would be a good reason to map my inputs to some high dimensional space and then do something linear in that high dimensional space? Yeah, so the you're not on the right side of the room, but I will accept your answer. Something linear in phi will generally be nonlinear in x. Okay? So this is a cheap way of doing nonlinear things by doing the same computations you would do for a linear method. Okay? So that's the kernel trick. And just to give you an example, if my feature space mapping is 1x, x squared, x cubed, right? I've mapped from 1 dimension to 4 dimensions. Now my functions that I'm learning, my decision boundaries, are going to be cubic shapes, okay, nonlinear shapes, and that's great, right? It's great that you can do that easily. So that's the kernel trick or the feature space trick, and it's a bit more complicated than that, and we'll see it in a little bit more detail, but that's the basic idea. Now the maximum margin trick says, okay, if I want to do classification and I have some data, okay, let's say I'm trying to classify these x's from these o's. Well, which decision boundary should I use? Should I use this one? Should I use that one? Should I use that one? All of these separate the x's from the o's, right? And maximum margin simply says, choose the one. I'll attempt to draw it. Okay, choose the one that has the largest margin. Okay, the margins should be symmetric. Okay, so the margin is the distance to the nearest points on the two classes. Okay, so it's sort of like choose the road that for which you can drive the widest truck through it. Okay, that's the maximum margin principle. Okay. So combining these two ideas, it turns out you can solve nonlinear classification problems using convex optimization. And that's a very beautiful kind of insight from the early 90s as well. Okay. So how does this relate to Gaussian processes? Well, here's just a review of the optimization function to solve this maximum margin problem. This is a soft margin support vector machine. It says minimize some quadratic norm on W. It turns out that minimizing the quadratic norm is equivalent to maximizing the margin, plus some term that relates to the classification error. Okay, so you want to minimize the classification error. This is called the hinge loss. Okay, the hinge loss looks like this. And basically, this is the sort of classic expression for a soft margin support vector machine where C is some regularization parameter. Okay? So now imagine that your function was just a linear function. Well, if we do the kernel trick, if we map from x to 5x, then another way of representing that is that we're mapping from x to some reproducing kernel Hilbert space, where any particular location x is represented by a function in that reproducing kernel Hilbert space. That's a very fancy way of saying we've mapped from a low-dimensional space to a high-dimensional space with some metric properties. Okay. Now, it turns out that the solution to, okay, so let's just look at this a little bit more carefully. Let's look at this, this linear dot product here. If we map x to this high-dimensional space, to take a dot product, we also need to map w to this high-dimensional space. So w is going to get mapped to some function in this high-dimensional space. And then the reproducing property of reproducing kernel Hilbert spaces in SVMs says that the dot product of k and f is just f evaluated at x. So putting that result back into the optimization function and going through a couple of linear algebra steps, what we get is that the kernelized support vector machine minimizes a loss function that looks like this. Okay? I've gone a little quickly through this derivation, but you can check all the steps if you want afterwards. Okay? Another thing that was important is when we map from W to F, the norm of W becomes the norm of F in the Hilbert space, which is represented as, in this form, 1/2 F transpose K inverse F. Okay, so that K is the kernel matrix. So by the way, K, the kernel matrix, is the same object as the covariance function or covariance matrix in a Gaussian process. Okay. So the support vector machine ends up resulting in a minimization that looks like this. It's a minimum of some quadratic function in F with the kernel matrix in there, plus for every data point, I indexes the data points. For every data point, some loss function associated with that data point. Okay. So that is the support vector machine loss function. Now, it turns out if you take the negative log of a Gaussian process classifier, the negative log likelihood of a Gaussian process classifier, it has this form. Okay? So it's exactly the same term. The first term is exactly the same. It's the function evaluated at your data points, transpose times the kernel matrix inverse times the same vector here, the same vector of function values. And now, instead of this term here, which is an expression of the loss for every data point, now what we have is an expression of the log likelihood for every data point with a minus sign. Okay? So again, we're trying to minimize this in the support vector machine. If we were doing maximum likelihood in the Gaussian process, we would be, again, minimizing the negative log likelihood, or maximizing this log likelihood here. Okay? So the noise model that goes from the function to the class label plays the same role as this hinge loss in the support vector machine. This regularization parameter doesn't appear anywhere in here. This is just an additive constant, which we can ignore. But otherwise, these two things look pretty much the same. OK, so what's going on here? Are these two things equivalent? Well, not really, because although they're based on the same idea, they're based on the idea of functions in some high-dimensional space. In the Gaussian process, we don't actually write it down as minimizing over the function value. We try to handle the uncertainty in f by averaging, not minimizing. So the picture to keep in mind, again, is instead of finding a single separator with highest margin, we consider the distribution over all reasonable separators, right? And then we try to average the prediction over that distribution. That's from the sum and product rule. Okay? So it's, maybe not a very big difference, but it does give you somewhat different predictions, and it gives you probabilities that you can interpret as probabilities, basically. Okay? The other nice thing is we can learn the kernel parameters automatically from the data. So I already told you that this kernel could be parameterized in terms of some hyperparameters. We can learn them from the data by doing maximum likelihood or Bayesian learning or something like that. It's very straightforward. We don't need to come up with any new theory for doing that. Turns out we can also learn the regularization parameter C without doing any cross-validation, which seems weird. How do you learn the regularization parameter? In an SVM, you would have to do some sort of cross-validation or something like that to learn that regularization parameter. In the Gaussian process, if you look at this, if I divide this whole expression by C, that's equivalent to dividing this kernel matrix. So the inverse of the kernel matrix by C. Okay? So C is simply a constant scaling on the elements of the kernel matrix. And that was actually one of the hyperparameters that I was learning automatically from the data. So sorry, I'm going to flip back. This constant scaling of the kernel matrix, this V0, plays basically the same role as C. All right? And that's something we can learn from data. Okay. So here is a picture to represent the relationship between a lot of these models. So we started from linear regression, and then I talked about doing the kernel trick, thus the orange arrows, so I could get kernel regression. I talked about doing turning a regression model into a classification model. So if I take linear regression and I follow the purple arrow, I get a linear classifier. For example, logistic regression would be an example of a linear classifier. If I follow the blue arrows, then I'm taking a non-Bayesian method, and I'm treating the parameters as being unknown and thinking about a Bayesian version of that. So that's Bayesian linear regression. So now if I apply this orange, blue, and purple arrows in different orders, I get different kinds of models here. So support vector machines are kernelized linear classifiers, okay? Or also a classification version of kernelized regression. Okay, that's two equivalent ways of writing the two adjectives in different orders, right? That's where the support vector machine lives. Bayesian logistic regression would just be simply a Bayesian linear classifier. Gaussian process regression lives here. It's a kernelized Bayesian regression model. And Gaussian process classification lives here. It's a kernelized Bayesian classification model. Okay? So that's the relationship between a lot of these different models. And it's useful to understand these because, you know, insights from non-Bayesian methods, if you follow the blue arrows, you can get equivalent Bayesian methods and vice versa. Insights from regression, you can turn them into different classification models, etc. Okay. So I'd like to do maybe a couple more demos of Gaussian process classification based on Carl Rasmussen and Hannes Nikish's GPML package. And maybe we can look at some questions there. So does anybody have any questions for me for now? Yeah.
So if we get in this classification task more information from Gaussian processes, when we should use SVM?
Why should we use SVMs?
Yes, because in many articles we see SVMs used.
Yeah.
Why?
So I don't use SVMs. Why do other people use SVMs? Maybe because they don't know about Gaussian processes. That's one possibility. Maybe because the software for SVMs is very good, and Gaussian process software has not caught up yet. And that's where this project is quite interesting, because they're coming up with better and better Gaussian process software. Maybe because SVMs are a little faster than Gaussian processes. That's also true. Sorry?
But in training or in classification?
In training, yeah. In classification, they're not that different. I'll show you some results later. There hasn't been any really good comparison between the two, to be honest.
For example, when I make some LDA, for example, to transform to another space and make some similarities to make classification. So
LDA meaning linear discriminant analysis.
No, linear Dirichlet allocation.
Okay.
Transform to another vector space and I make
Yeah.
I have a lot of different values because of these Monte Carlo methods and different a posteriors. So I'm interested in this is answer to this question that we prefer to use SVM and this determinant.
Well, no, but most of the Gaussian process algorithms are also deterministic. Yeah, almost every Gaussian process algorithm that's widely used is deterministic, and it just gives you an answer with error bars.
So in the code there is a variational method, yes?
Yeah, EP would be the one that people use for classification usually. Okay, so let me just find this code, show you some demos. MATLAB, GPL demo, okay. Okay, so do you want to do regression or classification? Huh? Classification? Do I hear classification? Okay, let's do classification. Okay. Okay, I need to make this maybe a little smaller. Or maybe I need to make it a little bigger. Okay, so this is a demo from the GPML toolbox. So it's very well documented. You know, it would take me a long time to actually read it because it's telling you exactly what's happening in the demo. So for demonstration purposes, we're going to generate a simple data set where the input of the data points for each of the two classes are generated by sampling independently from a Gaussian distribution. So press any key to continue. Okay. So here is the simple data set. We have blue points and red points, okay? And they're heavily overlapping. So it's a difficult nonlinear classification problem. And the contour lines show the ideal decision boundary, knowing the true distribution of the blue and the red points. Okay? Of course, not from the small sample, you can't get this ideal boundary. All right, so now we will fit a probabilistic Gaussian process classifier to this data using an implementation of EP, expectation propagation. We must specify a covariance function. We'll try to use a squared exponential covariance function. This is a very commonly used one. Blah, blah, blah. So it just ran, basically, actually. It ran while I was reading this. Actually, it ran before I was even reading this. Okay. Although the predictive contours in this plot look quite different from the Bayesian decision probabilities plotted previously, note that the predictive probabilities in regions of high data density are not terribly different from those of the generating process. So this is the predictions that it's giving you in terms of the probabilities. And you know, this line here, I think, distinguishes between the red class and the blue class, this sort of very light line here. So now it's optimizing the hyperparameters. That was for a particular choice of hyperparameters. Now it's actually optimizing the hyperparameters. So okay, that was learning the kernel. Okay, let's learn the kernel. It took a few seconds. It finished. And now this is the decision boundary that it comes up with. The actual decision boundary is this very faint cyan line, but this gives you the contour of probabilities everywhere. It's quite reasonable. Okay. Now we try a different covariance function, and that's what we get. So this is for a different covariance function. This is what's called the neural network covariance function. This is an interesting covariance function. This is the one that corresponds to an infinitely big neural network. Okay, so it runs in about 15 steps, and this is the answers that it gets. Not terribly different from before. We wouldn't expect any of them to be terribly different because they're all looking at the same data, right? So that's it. That's the Gaussian process classification demo. And what is the what else can I tell you about that? There are any other demos? Those are regression. Demo Laplace, maybe. Okay, so demo. Let's try that. I've never tried this one before. For demonstration purposes, this is the same data set, I think. Yep, same data set. Now, instead of using EP, expectation propagation, it's using Laplace. So like that picture, it's the same model, but just a different algorithm that's being used. How terribly different is it? Okay, not terribly different, really. Still converges fairly quickly, still gives you fairly reasonable answers. This is now with the neural network covariance function. To be honest, I don't know if I could tell the difference between the two. Okay. These are both deterministic algorithms. You could also do MCMC, but a lot of people don't like that. Okay. No, it's not determinate. I'm saying these two examples, EP and Laplace, are both deterministic algorithms for approximating the integrals. You could also apply MCMC, which would get you slightly more accurate, but would take a bit more time. And most people don't care about that. And they prefer not to have random numbers in their learning algorithm.
I read articles about this rate and Dirichlet allocation.
Yeah.
In these things, they usually used variational methods.
Yeah.
Mr. Minka used EP.
Yeah.
Another Mr. Griffiths used deep sampling.
Yes.
So I see that some person, some method.
Well, yeah, that's because, well, but it's sort of like it's part of the science here, right? In the sense, the same is true in the support vector machine literature. Okay, so somebody developed a support vector machine, then one person used one convex optimization method, another person said, oh no, I'm going to use SMO, I have a different method. Another person said, no, actually, I'm going to use some blocking method or, randomize perceptrons to optimize my support vector machine. So again, there's separation between the model and the optimization method. And it takes some time for the community to decide or agree what's a good way of optimizing a certain cost function. In the same way, it takes some time for the community to decide what's a good way of doing an integral for this particular model. And really now, if you ask anybody who works with Gaussian processes, they'll say, don't bother, for classification, don't bother with anything else. EP works really well. So then, you could just use EP. Unless you really want to, you really care about getting the very precise probabilities, and you have a lot of time. So then you use something like MCMC maybe. Okay. Does that answer that question, hopefully? Yeah. Okay. Any other questions? Yeah. Okay. So so that was a demo of Gaussian process classification. Let's talk about a few more topics, and then I'll tell you something related to some recent research we've been doing. This appeared, stuff I'll talk about at the end appeared in ICML 2013 last week, basically. So it's pretty recent. Okay. So this is slightly older work. This is about speeding up. Okay. This is about speeding up approximations. So a Gaussian process, in general, the exact algorithm for a Gaussian process involves determinants and inverses of an n by n matrix. And that is cubic in the number of data points. Okay? So order n cubed is not a good thing if you have large data sets. So there is a whole family of research methods involving sparse approximations to Gaussian processes. What that involves is approximating this n by n matrix by something that is exact on the diagonals and nearly exact on the off diagonals. And the way that's done is by approximating this n by n matrix by an n by m matrix, where m is very, very small, much smaller than n, times an m by m times an m by n matrix plus a diagonal n by n matrix. So that's the sort of picture to keep in mind here. Now, if you do that, yeah.
The last matrix just aligned because it's showing sort of weird.
Oh, going in and out, basically, yeah. This matrix here is a diagonal matrix, but it's not a multiple of identity. So the numbers might get bigger and smaller. Okay? All right. So so the point of doing this is that all of this is the sparse or pseudo-input Gaussian process or sparse pseudo-input Gaussian process, also called FITC. It's got several different names now. But the point of all of this is that we can make Gaussian processes linear in the number of data points and then quadratic in something that we get to control. So M is a trade-off parameter that we can control to get a speed accuracy trade-off. Okay, I'm going to have to turn off Dropbox, I think, because it's starting to annoy me a little bit. What's this? Dropbox. Go away, Dropbox. Quit Dropbox. Okay. All right. Okay, so so this is a Gaussian process, and there is a really nice review article by Quiñonero, Candela, and Rasmussen in 2006. It's a little bit out of date now, but it still covers a lot of the basic ideas behind how to go down from cubic to linear time with Gaussian processes. Some methods are exact, some methods, most of the methods are approximations. Here are some results from Naish, Guthman, and Holden, 2008. These are about the only results that I've seen where they directly compare Gaussian process classification with support vector machines on a bunch of different data sets using exactly the same kernels. And the interesting results here are, okay, this first column is just the regular Gaussian process classifier, which is somewhat slower than the support vector machine. These two columns are faster versions of the Gaussian process that are much more comparable to the support vector machine. In fact, they could be sometimes a lot faster than the support vector machine. So the interesting thing to note here is that in terms of in terms of test error, if you compare the last column to the support vector machine, often the Gaussian process is, or sometimes the Gaussian process is substantially better, something like 0.04 versus 4% versus 16% test error. Sometimes the support vector machine is a little better than the Gaussian process. But the other interesting thing here is this last column is the number of inducing points. This is kind of the sparsity level of the sparse Gaussian process as compared to the number of support vectors in the support vector machine. So here's something interesting. So let's just pick on one of these columns. So here the support vector machine gets an error of 0.226, but it needs 271 support vectors. The Gaussian process gives you an error of 0.230, which is very close to that, with only two equivalent of 2 support vectors. Okay, so you can get much sparser solutions actually with the sparse Gaussian process than the support vector machine. I think these results are interesting. I think it's preliminary. I would love to see somebody do a very exhaustive comparison of Gaussian processes and support vector machines, but nobody's done that yet. Okay. So I want to talk about a couple of other topics, and then I'll go into the research thing. Or let me just look at my watch. Maybe I should just go into the research thing. So one of the topics I wanted to talk about was feature selection. So how do you learn what features are relevant and what features are not relevant? In a Gaussian process, there is a nice answer to that, which is something called automatic relevance determination, which is if you have a kernel which has a parameter corresponding to each of your input dimensions, a length scale parameter corresponding to each of your input dimensions, then what happens is that when you learn that length scale parameter, it learns which input features are relevant and which ones are not relevant. So it's automatically doing feature selection inside the process of learning the kernel hyperparameters. Okay? So it's not like a wrapper system on the outside, or it's not like, you know, some other algorithm that you have to do for feature selection. It's part of the Gaussian process learning. Okay? So that's it sort of for Gaussian processes, and I'll tell you some recent research that we've done in a minute. So just to summarize Gaussian processes define distributions on functions that can be used for nonlinear regression, classification. They can also be used for things like ranking, preference learning, ordinal regression, a lot of these other kinds of data. They're closely related to many other models. We can derive them from Bayesian kernel machines, kind of a Bayesian version of SVMs, linear regression with basis functions, infinite multi-layer perceptron neural networks. They can also be derived from spline models. So they're fairly basic kind of object to look at. And compared to SVMs, they offer some nice advantages, especially for somebody like me who is interested in probabilistic approaches to learning. Okay. So learning the kernel and the regularization parameters without doing any cross-validation, integrating feature selection into the learning, and some fully probabilistic predictions and interpretability in terms of what's the prior over functions. Okay. So any questions about that? Okay, so this won't take, I don't think this will take very long. What I want to tell you about is just very recent research that we've been doing on something that we call structure discovery in Gaussian processes. Okay, so I don't have to really tell you about that, but let me tell you a little bit about what I mean by structure discovery. So this really corresponds to thinking about, you know, learning model structure from data, like how many states in a hidden Markov model, or how many sources in a independent components analysis model, or, you know, which input variables are relevant. All of these kind of very interesting high-level questions that are kind of at the core of machine learning. So we're going to talk about Gaussian processes, and I've just reviewed Gaussian processes for you. And in particular, I'm going to talk about this problem of learning this kernel. Now, the usual way people learn the kernel is to parameterize the kernel with a few hyperparameters, like, you know, v0, r, alpha, v1, v2, or whatever, and then learn those parameters by, say, maybe optimizing them as a function of the data. Okay? Now, what we're doing is something somewhat different. We're thinking of searching over a grammar of kernels to discover something about the structure in functions. So let me describe to you what that is. So here's the basic idea. If we take a few simple base kernels and we take two composition rules, kernel addition and kernel multiplication, then it turns out that we can generate lots of interesting structures. Okay? So I'll give you a bunch of examples here. This is a busy slide, but it shows you, this is from our paper that appeared in ICML 2013. And there is a companion paper by Andrew Wilson and Ryan Adams, also at ICML 2013, solving the same problem of structure discovery, but with a different method. Okay? So here is the basic idea. Our base kernels are going to be things like the linear kernel, periodic kernel, which models functions that are periodic. Linear kernel models linear functions. The squared exponential kernel models functions that have local variation. And this other kernel here called the rational quadratic kernel models functions that have variation at multiple scales. Okay? These are our base kernels. And this is the idea of kernel combination. If we take a linear kernel and we multiply it by a linear kernel, surprise, surprise, we get quadratic functions. Okay, we get a distribution over quadratic functions. If we take a linear kernel and we add a periodic kernel, then what we get is periodic functions with some trend. Okay? And similarly for lots of other things, if we take a squared exponential, multiply it by a periodic kernel, then what we get is functions that are locally periodic, but not globally periodic. A little bit like, wavelet decompositions give you something similar to that. Okay? So these are different ways of combining kernels in one dimension. But actually, we're not just combining them in one dimension. We're really looking at combining them where each of these base kernels can operate in different dimensions. Okay? So for example, we could have functions that are additive functions. So they're squared exponential in one dimension and squared exponential in another dimension. Or functions that have interactions, squared exponential in both dimensions. Or maybe functions that are, let's say linear in the first dimension, periodic in the second dimension, and something smooth in the third dimension. Okay? So all of that can be obtained by this simple addition and multiplication of kernels. And this is so then all we do is really search over a grammar of kernels. So we start from very basic kernels, given some data, and then the algorithm tries in somewhat greedy way different combinations of kernels by addition and multiplication. It computes the marginal likelihood or evidence for these different choices of kernels. And then it stops when it comes up with what it thinks is a good answer, or when it runs out of time. So here's an example of extrapolation. And this is sort of an interesting data set. This is a data set that a lot of people, when they talk about climate change, they talk about the carbon dioxide curve. This is technically called this Keeling curve. This carbon dioxide curve has been going up over the years, but it has some fine periodic structure in it as well. Okay, this is the carbon dioxide measured at the top of the Mauna Loa volcano in Hawaii. Okay, this is one of the data sets that climate scientists talk about a lot. The reason for that is that this guy Keeling had the foresight to measure this from many decades ago. So every a few months he's been measuring this thing. And so there's a good record from many, many years ago of this carbon dioxide level. And it's been going up, worryingly. But if we take data up to a particular year, like let's say 2004, if we fit a kind of standard Gaussian process with a rational quadratic covariance function, we get really good interpolation, right? We're fitting the data extremely well, but our extrapolations don't look so good, right? But what the algorithm does is it tries different combinations of kernels. So here is a periodic plus a rational quadratic. Now we're getting something a little bit even better. But, although it's getting the periodic component now in the extrapolation, it's not extrapolating very well, right? And finally, this is the answer that it ends up giving us, which is a long-term squared exponential trend times periodic plus rational quadratic. And now the extrapolations look like this. Okay. And by using marginal likelihood, it basically ends up preferring this explanation for the data than these two explanations. So the nice thing here, there are two nice things about it. One of them is it actually ends up predicting better. So on measures of test performance, this does pretty well. But the other nice thing is it gives us a kind of interpretable string for what kind of kernel this data wants to use. Okay? So that's why it's discovering the structure of the kernel somehow. So here is another data set. Sorry, this is a bit too small to see, I think. It's maybe a bit fuzzy. I don't know if I can zoom in. Oh, yeah, I can zoom in a little bit. Sorry. I zoomed in so much, I can't see anything anymore. Okay. No. Oh, I'm on the wrong page. Okay, so this is a data set. It's a little fuzzy still. This is a data set of airline passengers over the years. Okay, so also another one of these data sets that's kind of interesting because there is a general growth in the number of airline passengers, and then there's some seasonality, like, you know, this is maybe that's Christmas, I don't know, like maybe that's Easter or something. You know, there's some major holidays or something like that. Okay, so and then this is the prediction that the model comes up with. It says this is the kind of kernel I want to use: squared exponential times linear plus linear times periodic plus rational quadratic. Okay, so this is the explanation. And when you decompose this, you can actually decompose this into a linear trend plus a periodic component plus two different noise components. Okay? And so that's what the model comes up with. When it comes to doing prediction, it ends up predicting much better than using one of the standard kernels or using one of these kind of multiple kernel learning methods from the support vector machine literature. So this is kind of the predictive performance in mean squared error. This is a negative log likelihood. Higher is better here. Or actually, negative log likelihood. Lower is better for test data. And some of these are high-dimensional problems. So the pictures here are for 1D time series, but these are for higher dimensional problems. Okay. So the basic idea behind all of this is that we really want to do structured learning on kernels to do both something that's good at prediction but also more interpretable. And I think it's important for machine learning methods not just to be good predictive black boxes, but also for us to be able to understand what's inside those black boxes and to get some interpretability. And this is part of a kind of larger project that I'm running on trying to build sort of an automated statistician that tries to understand data, you know, and interpret it for us. And I want to thank the sort of the main contributors to this work, which are James Lloyd, Andrew Wilson, and David Duveneau, who are the main authors of the two ICML papers that I talked about. Okay, great. All right, so I think we're done for today.